Okay, so we're going to continue on. Last time we did the spectral simulation of the particle in a box, but in a small, like just two wave functions, right? Or just two quantum states. And I talked about like a high resolution spreadsheet that I have. And today I want to talk about or unpack a little bit more in depth this thing called spectral convolution. So we'll see that word in the notes here in a second. But this is, we use the particle in a box just because we could understand it from the very beginning, you know, an electron on a wire with the infinite potential to keep it on that wire and zero potential in the middle. And we could do the algebra and the calculus associated with that all the way up through the simulated spectrum. But we're about to leave that model and get into real molecules this week. So you saw online, perhaps through Blackboard or your email, that I won't be here Wednesday, but that we'll be putting some of this work into play on Wednesday. I have a video that I made yesterday for you guys that is posted on Blackboard for you to watch for Wednesday morning's lecture. But we're going to start getting the laptops out. And on Wednesday, if you'd help them, like bring the key down and open the laptop cart and get everybody laptops on Wednesday. Okay. And you can calculate Gaussian. And what I'd like for you to do is the example that I calculate for Wednesday is benzene. Okay. And so what I would like for you to do is to calculate other derivatives of benzene. And let's use fluorine because it's a smaller number of electrons, a smaller element. It'll be faster than chlorine. And so like you might do just like, you know, chlorobenzene and maybe like 1,2 dichlorobenzene and 1,3 dichlorobenzene and 1,4 dichlorobenzene, right? And so, and then to do trichlorobenzene all together, you know, 1, 2, 3, and then 1, 2, 4, and then whatever, you know, y'all come up with all the different, or I said chloro, I mean fluoro, all the different derivatives of fluorobenzene that you can come up with and try to figure out, and you may have to help each other in terms of the point groups, but try to get Gaussian to use symmetry to find those point groups, like if it's C2V or like the D3H or something like that. There's a symmetry tool in Gaussian, and I may pull it up here in a bit and show you what I want you to do. And you're going to get the vibrational frequencies for that. And then we're going to continue that work on Friday, so you don't have to do it all on Wednesday. But on Wednesday, as a group, y'all can start to use Gaussian, and then on Friday, you'll have tons of questions for me, okay? And then we can work together on Friday, and I can answer your questions, and we can start to simulate spectra of real molecules, okay? I'm going to cover some of that today, though, and on the lecture for Wednesday. Okay, so this simulation process, we've talked about it before, but I've got it lined out here, sort of outline form. You have the Schrodinger equation, the wave functions, the energy equation. Then you calculate the transition integrals, whether it be a transition dipole integral for absorption and emission, or some sort of polarization integral, x squared, y squared, xz, for Rayleigh and Raman scattering. And then that gives you your selection rules. And you can calculate your transition equation. Then you can take into account the Boltzmann distribution to calculate the thermal population of your energy levels. And then you can put this last piece, is the important piece for today, the line shape on it. So we're going to talk about the line shape functions today. So we'll go through this first piece, the first parts of this outline really quickly. So we've done this over and over again, the Schrodinger equation on the wave functions. We get the energies out. It's related to the curvature of the wave function. But let me talk a little bit about what we did for this particle in a box in terms of taking the derivatives. Notice how if I'm going to take the derivative of this function numerically, it's just the delta y over the delta x. So I can calculate that point, delta y over delta x. You know, it's this difference here, so this minus this divided by this minus this, right? That's the slope. We call it rise over run. Okay. Now I've calculated that number. Where do I put it in the table? Okay. I can put it here. Let's say this is psi prime, right? I could put it here, and so I'm taking the forward derivative and putting it here, right? So I've calculated the forward derivative and I'm putting it here. Or I could put it here. That would be the backwards derivative. So I'm calculating this difference and I'm putting it on the front point, the next point. Both of those are going to mess up the symmetry of the wave function. So the forward slope, if I calculate the forward slope, I'm putting that at 0. So I'm taking this x plus 1 and y plus 1 and subtracting x and y, taking the ratio, and if I put it on 0, I'm calculating the forward slope. Is the slope at 0 negative? No, it's not. What if I calculated the backward slope? I took x and subtracted x minus 1 and y and subtracted y minus 1. That's the backward slope. If I put that at 0, I screw up the symmetry too, because the slope at 0 is not positive. The slope at 0 is 0. And so what we're doing is we're calculating what I call centered derivatives. So I'm taking the y plus 1 and subtracting the y minus 1, and taking the x plus 1 and subtracting x minus 1. And so that's the centered slope. So then I'm losing a data point on either side. I'm taking the y plus 1 and the y minus 1 and subtracting that, taking the difference, and the x plus 1, x minus 1 and subtracting that, and putting it on that center point of 0. Make sense? That means for over here on the side, I need some extra data points on either side. To take the second derivative, I'm going to need 2 data points on either side of my box. And when I take the first derivative, I've lost one set of outer points. When I take the second derivative, I lose the next set of outer points. And then I have accurate slopes of all my wave functions. So there's just 3 ways to calculate that slope: forward slope, backward slope, or centered slope. And that's what we're doing here. And so then that allows that blue wave function to cross 0. The slope crosses 0, and that maintains the symmetry of my wave functions and my wave function derivatives. So it's just a little bit of a nuance into how I calculated the derivatives in these numerical methods. Okay. So we get our energies. We did the matrix multiplication, only now we have a 15 by 15 matrix because I have 15 quantum states in the high resolution worksheet. We get our energy patterns. These are our eigenvalues. We have the transition moment integrals. So we did these for X, Y, Z polarized light and Rayleigh-Raman scattering. So we have the X times our wave function. So here's our perturbed wave functions. And we calculate those integrals. So again, that's transpose 15 by 100 times a 100 by 15 gives us a 15 by 15. And we end up with these patterns that we saw last time, which are our selection rules. We can use these selection rules to calculate our transition equations to say, well, we'll do a delta n equals 1, delta n equals 2, or 3, I should say, and 5, and calculate our transition equations. We calculated these in homework by, in general with delta n's. And now let's talk about the Boltzmann distribution. So the thermal population. So here's our equation. It's the degeneracy term times this exponential, and it's based upon the ground state. So it's always relative to the ground state. And so when you are in the ground state, this difference is 0, so you have e to the 0, which is 1. So the Boltzmann factor for the ground state is 1. And for all of the other states, it's going to be less than 1. So these are probabilities relative to the ground state. So we can look right here, this Boltzmann factor. So at this particular temperature that I have, I don't know exactly what it is for this screen, but we have, relative to the ground state, a 95% chance of being in the first excited state. Now notice these are not normalized probabilities, okay? These are relative probabilities. because if they were normalized probabilities, they would all add to 1. Okay, and they don't all add to 1. This is 1 by itself, and this is 95, 0.95, 0.87. So if you wanted the true percentages, like the true distribution, then you would take each one of these and divide by the sum of all of them. Okay, and so that would give you your true percentages. And we do that in the thermodynamics course. But these are the relative percentages. So compared to the ground state, I have a 65% chance of being in the 5th state compared to the ground state. So not as likely. Okay. And then we can calculate our stick spectrum, which is just that Boltzmann factor times the transition moment integrals. So this times this gives this. And so notice that the transition dipole moment integral goes up with n. So here it's 1.98, whereas in the ground state is 1.57, but it's actually smaller in terms of its predicted intensity because it's the Boltzmann factor times the transition moment integral gives us our predicted intensity. Now, we call this a stick spectrum because we could plot these and we would have the stick spectrum. This is what Schrödinger did in his paper on the hydrogen atom. He plotted the stick spectrum of his transitions. He calculated the intensities and the transition energies, and he was able to plot it and see that it matched the hydrogen atom spectrum. Have all of the quantum numbers here assigned so that you can understand these. We can go back into the notes to relearn the vocabulary. We have the fundamental, we have the hot bands and the overtones. Okay, then we have versus wavelength. And so we can convert that energy, the delta energy, into wavelength. Okay, so we can swap that around, and lambda is equal to hc over delta E. And then we have our wavelength spectrum. So this is the stick spectrum versus wavelength. Now, we have these sticks, and we want to put a line shape on them. So we're going to have a particular line shape for our spectrometer for every transition. And they're going to overlap. So this one is going to overlap with this one. And so then the resulting curve will go like that, right? Because we have this contribution here plus that contribution here gives you the overall composite spectrum. And so this is what's called convolution. So this line shaped spectrum, this is our experimental apparatus, and then the uncertainty of nature. And so we have these different line shapes that we can use. So this is the Gaussian line shape. You know, the Gaussian is kind of a minus e to the minus x squared. So we have that behavior here. X in this case is the distance of our spectrometer wavelength, or a spectral wavelength. I'll say from the monochromator. And so we have a resolution factor, our uncertainty in wavelength. We have the transition wavelength, and then we have where the monochromator is currently set. Does that make sense? So as we scan our monochromator, we're at a particular wavelength right here. And we can say, what is the intensity of that peak at that wavelength? And then we move our wavelength again, and we calculate the intensity at that wavelength. So for every transition, we scan our monochromator along, and we see where that peak will be, including its width and, you know, as far how it drops off with wavelength. So that's why we're putting this. So if we're here at 450, you know, lambda equals 450, the center wavelength is 550. Make sense? And then our line width is right here. This is our line width, delta lambda. So we have these three factors in this equation here, and it gives us this intensity value right there. And if we move the monochromator a little closer to the center wavelength, let's say we move it to 500, now it's calculated as that intensity. You see what it's doing? So it's telling us the response of our spectrometer to that particular transition. Make sense? Okay. Now, a Gaussian is just sort of like the normal distribution of random fluctuations. And that's most of the time what's going on in our molecule. We have vibrations and crystal structures, and everything's in a slightly different environment. You think about a molecule in a little tiny crystal piece, and then a molecule on the surface of an amorphous solid, and a molecule kind of out on the tip of an island or something. So all of those molecules are in random positions, and because they're in random positions, their transition wavelength is randomly spread out in the shape of a Gaussian. Does that make sense? Think about if you're taking a spectrum of a molecule, all the random places it could be in that crystal structure or powder or whatever. Okay, so Gaussian shape is pretty common. If you have something that, like a gas phase molecule, cold temperature, a super high resolution spectrometer, you might have this peak shape, the Lorentzian. This one is the one that you get theoretically if you take the Heisenberg uncertainty principle and apply it to the stick spectrum and calculate what the uncertainty principle would give you in terms of the peak shape. This is the peak shape that you get. Okay, it's not a randomly fluctuating peak shape. It's what we call the natural line shape. So you could have a Lorentzian. Same thing. We have the wavelength of the monochromator, we have the transition wavelength, and we have the resolution of the system. Okay, and it's going to give us this. So instead of our absorbance being big, it's BIL, so Bill for the Lorentzian line shape. Okay. And then we might have a Voigt profile. So let's say your spectrometer is not quite at the resolution of the natural line shape, is still showing some Gaussian character. Well, we can just mix in both line shapes. This is really ugly in terms of the spreadsheet formula. You've got both of those line shapes in there with another constant thrown in, and it's pretty ugly. I don't even know that I have it in any of my spreadsheets, okay, because it's so ugly. It could be done, but the point is, if you really were trying to model your line shape very well, you might need to use a Voigt profile. And then the last one is the log normal line shape. This is kind of an ugly equation. It's got the monochromator wavelength here. It's got the transition wavelength. It's got the uncertainty, spectral resolution. But it also has this asymmetry parameter, rho. And if we look at our shape here, notice our peak is asymmetric. So it's got a short side and a long side. And so we have the in this case with it tailing low, we have this if we take the half height and we draw a line across, we've got this point here on the x-axis and this point here on the x-axis. And that allows us to calculate our asymmetry parameter. So we have the high wavelength minus the center wavelength divided by the center wavelength minus the low wavelength. And so the thing is, this can't equal 1 for two reasons. One, this is the function you would use to model asymmetric line shapes. And so if you're trying to model a symmetric line shape where it's right in the center and it's the same on both sides, use a different function. Second thing is that you're then going to have the log of 1, which is 0, in the denominator. Okay, and so that's going to blow that up, and you're going to have again the log of 0 here. So we're going to have problems with our natural logs with a symmetry parameter of 1. It can be close. It can be like 0.99. So if you wanted to get close to a symmetric peak, you could do 0.99. But if you do 1, it blows up. So those are the three line shapes, really 4 with the Voigt profile, that that are typical in science. And so you may or may not come across them. It just kind of depends upon if you go into spectroscopy or not. If you're in another subdiscipline of chemistry, you probably won't come across it. But you might see it in a paper. Like if they model a particular high-resolution spectrum, you might see them say something like a Voigt profile or a Lorentzian line shape, and then you would have a resource in the notes to go back and do some research on what that means. So now let's actually make it happen. We have our delta lambda up here, okay? It's our spectral line width here. So that's the delta lambda term in all of these line shapes. And then down here, this is wavelength, so this is lambda here. And then we have our transition wavelengths. So we have all three pieces for our spectral, our line shape functions. We calculated all this with the particle in a box. We have the peak number, we have delta n. So in all of these are delta n plus ones. We have this lower state is 1 to 2. So this is the fundamental here. And then this whole group here are the hot bands. But what I want to emphasize here is we can take that height, we can take the wavelength, which is the center of our peak, and we can take those wavelength values and our uncertainty, our delta lambda, and we can calculate that line shape function underneath that transition. So we just type in that Gaussian formula or Lorentzian or whatever, but we'll use the Gaussian for all of our work. And we then plot that function, or they put that function right below the transition. So we have a center here, a height, and that line shape function as a function of this wavelength over here. So this is our monochromator. And our spectrometer. Okay, so as it scans along, you notice how if it's scanning along at these wavelengths, it has zero intensity from these peaks because they're far enough away that they just don't absorb at that wavelength. This one's starting to absorb though, 7 to 8, you see 0.1. So it's getting 0.1 absorbance from that particular transition. And if we move the monochromator down, it gets 0.1 from the next, and it'll slowly grow in. Now, for the second transition and third and fourth, we calculate a line shape function for every one, and that's called spectral convolution. So this right here, we're putting a line shape on each stick. So that's what's going on right there, spectral convolution.
So we're just inflating our stick into a balloon or something.
Yeah, we're just inflating those sticks into a line shape. Yeah, and then because now they overlap, the sticks don't overlap; they're infinitely thin. You know what I mean, right? And so if we make them thicker, if we balloon them out, then now they overlap and they will add intensity. And so there might be a wavelength in my monochromator that I'm sending it through, and peak number transition 7 absorbs on this electron or whatever, and transition 8 on that electron, and transition 9 on that. So there's lots of options at that wavelength for different excited molecules, electrons, atoms, ions to absorb at that wavelength. And you don't know which transition each individual photon is going to be absorbed by, but there's a probability that it's going to be absorbed by something. And so if you're at that part of the spectrum, there's a really high absorbance intensity because you have so many options. All your photons don't make it through because they get absorbed by something. And then we sum up all of the contributions of every peak for our total signal.
That was my question.
So this right here is actually the spectrum of the whole thing. So this right here is the simulated spectrum.
So like that's what you're going to plot and see.
Yes.
Okay.
but it's very visual. And that's why I like the spreadsheet. We could do this in Mathematica or MathCAD or whatever. We could give it a list of transitions and produce the spectrum. But I like this in a spreadsheet because you see the contribution for every peak. So I can see that, you know, peak number 4 is giving us no contribution here, but peak number 7 was giving us some contribution. And so we can see individual transitions on the right over here. So these are the individual transitions, and they sum together to give me my simulated spectrum. And so this is what we end up with. And now I have everything plotted on here. I have the sticks. So I have that, you know, that, let me reset. So this is the transition dipole moment integral result. This right here is I, but then this is that G, the Gaussian line shape. And notice right here, if my monochromator is sitting at whatever that is, 430, I have two possibilities to absorb my photons as they're going through the sample. And so the composite spectrum, the overall simulated spectrum, is the sum of both of those contributions. Look over here. This right here has the contributions of all of these possible absorptions. And so even though every one of those is pretty small in terms of the probability, they add up to where that's the strongest absorption spot in my spectrum. And this is very typical, especially in UV vis spectroscopy, that you see really broad peaks because there are so many possible absorptions underneath. All of the vibrational modes will create new electronic absorption possibilities. So if the molecule is excited vibrationally, you have lots of, quote, different types of molecules in there, lots of different electronic wavelengths that could be absorbed. Whereas over here, if I set my monochromator to 700, I essentially have no absorption, okay? Because all of the absorptions are at lower wavelengths than that. So what I'll do is I'll pull up the spreadsheet and you can see it in action now. Okay. Let's go over here. Bring up Excel. No. It got moved somehow, so just bear with me. Here we go. Yeah. Okay. Yeah, that looks good enough. Okay. So what we have here is the, it's not coming across? Huh, wonder what happened. Why, oh why? Okay. Then we got it now, okay? All right, so this is the, quote, high definition particle in a box. And here I have the box length. I'll zoom in a little bit. Okay. And so here I have the box length, I have the mass. We could change to a proton if we wanted, and so on. Here's the temperature, starting wavelength, ending wavelength, and spectral line width. Let's just look at this comparison to analytical results. You know, last time we only had two wave functions, and we only had 10 increments in our box. And we had pretty bad errors, right? Do you remember that numerical errors? Here I have 200 divisions of my box. And look at my errors now, 0.03%. So I have the numerical solution here, the analytical solution, and they're pretty close. So because I've taken my box now, I've reduced the numerical errors by putting 200 divisions in my box. I've divided it and put 200 points between L plus L over 2 and minus L over 2. Let's look at the spectrum, though, since we're talking about this simulated spectrum. Here's the spectrum that we just saw in the previous slide. Okay, and let's predict what happens to our transition wavelength when I lengthen the box. Okay, now we know what happens with the energies, right? Because the box length is in the denominator. So if I lengthen the box, my energy levels will crush down. Okay, all right. Now, what is spectroscopy? Spectroscopy is differences between those energy levels. So what happens to the differences if my energy levels shrink? They become smaller as well. Okay, so I have smaller arrows. Now, how are the arrows, the differences in energy, related to wavelength?
Smaller energy, larger wavelength.
Yeah, smaller energy difference means longer wavelength. Everybody believe that, okay? You follow the logic, okay? Now let's increase our box length. So look at this, our wavelength here is 538 nanometers, 538. You want to write that down, somebody? Write 538. Okay. So we'll come up here, and we're just going to increase it a little bit, okay, to show you how sensitive it is. We'll go to 7.5, okay? It went from 538 to over 600. Now it's at 618. Yeah. So this is great for spectroscopy if you think about it. This is showing us how sensitive spectroscopy is to the size of the system. And that's how we used spectroscopy to get the geometry of molecules, bond lengths, bond angles. Okay, because it's incredibly sensitive to the size of the system. We change the size just a little bit and we get a huge change. L squared, right? Okay, let's go back to 7. Okay, now M is in the denominator, so if I increase M, we're going to see a big shift to our wavelength. So let's go to our proton mass. Can somebody help me with that? Yeah, go ahead and Google it for me. I never can remember the proton mass.
Net was 1, but I think it was about
10 to the negative
1.67 times 10 to the negative 27.
27. Okay, yeah. So 1.67 E minus 27. So you can look at how I entered that in Excel. That's a way to type in times 10 to the. Okay, so it works. Okay. Now look, our thing is broken because now we're at 1 million nanometers for our fundamental. Yeah, that's right. Yeah, millimeters. Yeah, millimeters. Okay, and so our plot is all screwed up because we're only plotting in nanometers from 10 to 650 nanometers. Okay. And so we don't have the curves, but we have the stick spectra. Okay, so very sensitive to mass. Let me just do
It's interesting. If you look at analytical and numerical, it completely almost shrunk a lot of the error values because it less off the sensitivity, so it's 0.004, 0.04. Whereas if some of the discrepancy between 1 and 2 was actually like, I think,
Oh, yeah.
or something like that.
Yeah, I did Control Z. Yeah, so
Yeah, see,
yeah, big differences. Yeah. Okay, now let's look at temperature. Do you predict that temperature will change the wavelength?
It should change the wavelength.
Yeah.
It will change the intensity.
It will change the intensity.
Is temperature in the energy equation?
No.
See, you know this. So think about the equations. This is what I was trying. The reason we go into the particle in a box is for you to just know. And it doesn't matter now if it's the vibrational spectrum or the electronic MO diagram or whatever. Temperature has no effect on the energy differences. No effects. Not in the Hamiltonian. It's not in the wave functions. It's not in the energy equations. Okay, so let's change the temperature. We're at 500,000 Kelvin because this is visible spectroscopy. So we had to really crank up the temperature. Give me a temperature. What do you want to do?
It's at 0.
Add a 0. Oh, okay. Yeah, let's go up. I didn't think about that. So now we're at 5 million Kelvin. We're on the sun. Okay, our poor electron. Yeah. So it looks like it shrunk in intensity, but I think it just got bigger down here. Okay, so let's look at that. So we had 14 as our peak maximum. Our fundamental is at 1.58. Let me do Control Z. We'll go down. Yeah, so this is still at the intensity of our fundamental did not change. It's still 1.58, but up here the hot bands went up, and so this went up from 5 to 14. So our peak maximum in all this overlapped region went up dramatically. Now you might see a shift of that peak maximum. Let's look at its center wavelength. Write down 129 for me. Okay, so the center wavelength of our peak maximum here is 129. But notice that's an overlap of a whole bunch of different transitions. Yeah. If we change the temperature and we change the population of those transitions, then we might see a wavelength effect from temperature, but it's because we have overlapped transitions. We're not changing the transition positions, we're changing the populations of those. And so let me do a redo on that. So we went back and added our 0. It was at 129. Come on, get on there. It's at 93. Okay, so it did shift a little bit because we changed the relative populations of those peaks. And so, but you know, in terms of the actual transitions themselves, they have not changed position. The fundamental is still at 538. It hasn't moved with respect to temperature. Okay, let's go down in temperature. Let's go to 50,000 from 500,000. And we are losing our hot bands. They're not hot. Molecules cooled down from 500,000 to 50,000.
When will you release the temperature?
Pardon?
I don't understand that. I don't get that part.
The temperature is the Boltzmann distribution in how many of these excited states for the hot bands to occur, like from 2 to 3 or 3 to 4, we have to have molecules in 2 and 3. And so if we cool the temperature down, the probability of being in level 3 goes to 0. So we will lose that peak. Yeah, does that make sense?
Yeah.
And so look at this. These peaks over here are gone. They're still there, but there's no molecules or electrons. No electrons in those quantum states because of the temperature.
So, those peaks are called the overdose.
No, okay. These are hot bands.
Yeah.
This one is the fundamental.
Yeah.
This is the first hot band, the second hot band, the third hot band. Now, one of these down here is an overtone. They're on top of each other. Yeah. We can go back to this right here. You can see those green and red bumps are the overtones. The blue ones are the hot bands. This is the fundamental. Okay. Yeah. But look how much temperature had an effect. Now, this is interesting too, because this means we can use spectroscopy to measure temperatures. Really. And so one of the most reliable, but it is controversial, one of the most reliable ways of measuring global temperatures, mean global temperatures, is using the spectrum of the atmosphere. And you can get a temperature of the atmosphere using spectroscopy. So that's pretty cool. The reason I say it's controversial is because it contradicts the land stations, the land-based temperatures. Okay, and so there's sort of set up, which one do you believe, right? And so there's a bit of controversy over which one you believe, the land temperatures or the atmospheric temperatures, and measuring the temperature record in the past. Okay. Now let's look at temperatures some more. If we go to 1,000 Kelvin, what do you predict? Do we have any hot bands?
Yeah.
Just the fundamental. Yeah. And why can we not get rid of the fundamental? Let's go to, I won't do 0 Kelvin because it breaks the Boltzmann distribution, but I'll go to 1 Kelvin. Close enough, right? No change. And so that's a common mistake when I say, what happens to the spectrum when you go to 0 Kelvin? And I say, all the peaks go away. But no, we can't lose our matter. All our electrons are in the ground state, or our molecules or whatever. They're going to be in the ground state, and they're going to have that fundamental absorption, but even at 1 Kelvin. But you can see why cold temperature simplifies things. It takes away all of this other transition. We still have an overtone over here. You can't really see it, but it's there because it's the 1 to 4 transition. It's still in the n equals 1 starting state. Now let's look at spectral resolution. 500,000, let's go back to that. So this spectrometer is not too good because it's got like a line width of like 40 nanometers. Let's make it 20. Okay, now we used to see like one peak, a shoulder, and a big peak. Now we're getting 2 resolved peaks, a shoulder, and some more, things. We haven't changed the temperature, haven't changed anything. Let's go to 10 nanometers. And we're able to resolve these. There's still some mixing of these, but this one is starting to become resolved. And so we can increase the resolution of our spectrometers and get more peaks and assign those peaks.
Spectrometers that have that resolution?
Oh yeah. Especially in the UV vis, there's some that are like 0.15 nanometer resolution. Yeah. And so what you'll probably be governed with is just your spectrometer won't be the thing that limits your resolution. It'll be the molecules themselves, and like I said, the random environment of. So let me just sort of put a caveat on what I've been saying. Let's say this is the spectrometer resolution or spectral line width, but that may be not limited by your spectrometer, but by your molecules. So like if you have an amorphous sample, it's going to have wider peaks than a crystalline sample. Think about all the molecules in a crystal. They have the same environment, so they have the same transition wavelengths. If you have a molecule in an amorphous environment, you're going to have a wavelength here and a wavelength here and a wavelength here. So the fundamental transition for this molecule on the outside edge is different than the fundamental transition for this molecule on the interior. And the interior looks different for all the different molecules because you have fractures and all kinds of garbage in the whole area, impurities. It doesn't dramatically change the wavelength. It's still the fundamental, but it spreads out the peak with amorphous. You get it in a crystal environment, you get really sharp peaks. Liquids are crazy. Really broad peaks in the liquid. You freeze it in a crystalline form, narrow peaks. You put it in the gas phase, really narrow peaks. Because now you have a molecule that's just in a field-free environment. And all of the molecules are the same. Because it's really rare to get a spectrum of a molecule right when it's colliding. Right? Most of the molecules you get in a gas phase spectrum don't know there's anybody else in the room. And that's why Gaussian calculations and gas phase spectra match so well. Because the Gaussian, you're calculating for a single molecule, and in a gas phase spectrum, you have a spectrum of a single molecule. A billion of them, but they're all behaving as if they're single. Make sense? So this is the super HD spreadsheet, and way out here, this is the simulated spectrum, and you can see here's all of the convolution. So let's look at, like, here's my wavelength. Let's scan the monochromator and look over here to the right. So I'm just going to take a spectrum and scan my monochromator. You see the peaks come in? So I'm scanning, and I saw all those peaks come in one at a time, or sometimes multiples. Does that kind of help you understand what's going on? Yeah. Okay. So that's, I'll make this spreadsheet available to you just for fun. You can play around with it, okay? And then next time you'll take this, you'll see from the Wednesday lecture, you'll take this kind of page that I have here, and we're going to delete all of this stuff related to the particle in a box, and you're just going to get your transition wavelength from Gaussian and your intensity from Gaussian. Those are the only two things you need to do this using the software from Gaussian. You just need to know where my transition is and how strong is it, and then you can simulate the spectrum. Okay, all right.